Hello everyone. Today I will talk about a beautiful unifying concept in mathematics called group theory. Group theory can give a framework for many simple and complicated situations in life. Starting from the integers to clock arithmetic to symmetries of regular polygon to various other more complex situations. For instance, the standard model for particle physics uses group theory and its representations of groups very heavily. So we start with a very simple example of a group. So you all must have heard about the integers 0, plus minus 1, plus minus 2, plus minus 3 and all. So it's an infinite set and you can add integers and the result will still be in the set Z, right? We need not mention subtraction separately because the negative numbers are already there. So 5 plus minus 3 is 5 minus 3. So you needn't mention subtraction because plus is there and the negative numbers are there. What you notice about this system of integers with the operation plus, that it has four very interesting properties. One is closure. Given two integers a and b, a plus b is again an integer. Existence of identity. There is an element in Z, namely 0, such that a plus 0 is a for all a in Z. Similarly, 0 plus a is a, and this 0 is called the identity element. Similarly, existence of inverse. Given a in the set of integers, there is an element minus a again in the set of integers, such that a plus minus a is 0. Similarly, minus a plus a is 0. So 2 is the inverse of minus 2 and minus 3 is the inverse of 3 and vice versa. Okay. And there is a fourth property called associativity. So that says if you add b and c first and then add a to it, that's the same as adding a and b first and then adding c to it. Okay, so this pairwise addition, the order doesn't matter. Second example, we take the set of fractions of the form p by q with p and q from the integers such that p is greater than 0 and q is greater than 0. So I take only positive integers p and q, form the quotient p by q, fractions p by q. Okay, and you notice that p is not equal to 0 and q is not equal to 0. So even though 2 by 3 or 3 by 5 are there in the set, but 0 by 3 or 18 by 0 are not in the set. We do not allow 0 by q or p by 0. So 0 and infinity are not in the set. We denote this set by f cross. Let us define multiplication operation into on any two fractions. So it's the usual thing, 2 by 3 into 3 by 5 is 6 by 15, or you can reduce it to 2 by 5. 3 and 3 cancels. So it's the usual into. So f cross and into has four very interesting properties. The same, closure. If you take two fractions, multiply them, it's again a fraction and it will satisfy that if p, q, r, s are non-zero, then p into r and q into r, s are also non-zero. Similarly, existence of identity. There is an element in f cross, namely 1, such that 1 into p by q is p by q and p by q into 1 is p by q. Existence of inverse. Given an element of f cross, say p by q, there exists an inverse q by p, such that p by q into q by p is 1 and q by p into p by q is 1. So for example, the inverse of 2/3 is 3 by 2. Similarly, the inverse of 3 by 5 is 5 by 3. Inverse of 5 by 3 is 3 by 5 and so on. Okay. And associativity property also holds. So now we are in a position to define a group. Definition of a group. A group is a set of elements G with operation circle such that G circle has the following four properties. Closure. Given two elements A and B in G, the element A circle B is again in G. Existence of identity. Given any element A in G, there is an element E in G such that A circle E is A and E circle A is A. Existence of inverse. Given any element A in G, there is an element called the inverse of A, denoted abstractly by A to the minus 1, such that A circle A inverse is E and A inverse circle A is E. Associativity. Given three elements in G, we must have A circle B circle C is the same as A circle B circle C. Note, in general, we do not require A circle B is B circle A for all A and B. In fact, A circle B is equal to B circle A for all A and B is the commutativity condition. In the case that this holds, we say the group is commutative. Thus, commutative groups have A circle B equal to B circle A for all A and B. Examples? Well, Z plus F cross into are groups and they are commutative groups. The first one has operation circle is the operation plus. Second one, operation circle is into. And as I said, they are commutative because 2 plus 3 is 3 plus 2. Similarly, 2 into 3 is 3 into 2. So later on we will do examples of non-commutative groups. But as far as this lecture is concerned, all groups are commutative. Examples of finite groups. Let us take example of clock arithmetic. So your set is 0, 1, 2 till 23, which stands for the hours from midnight to 11 p.m. As you know, 11 p.m. is 23 hours, midnight is 0, 1 a.m., 2 a.m. and so on, right? Notice these are all possible remainders of any number if you divide it by 24. So for example, 54, it leaves a remainder 6 on division by 24 because 54 minus 2 into 24 is 6. If the number is divisible by 24, the remainder is 0. Okay. Let us do a special arithmetic on this set G. Take any two integers in G, add them, and if the result is less than 24, just keep it as it is. If the result of the addition is more than 24, then divide by 24 such that we are left with a remainder which is obviously something from 0 to 23. Then the remainder is in G. This is called addition modulo 24 arithmetic. So for example, let's take 2 and 4. You add them to get 6 and that is there in G. Let us take 22 and 23. If you add them, it's 45. If you now divide by 24, the remainder is 21, right? So if you divide 45 by 24, the remainder is 21. So this is called addition modulo 24 arithmetic. Okay. So the circle in this case is denoted by equivalence mod 24. So 6 is equivalent to 6 modulo 24, 45 is equivalent to 21 modulo 24. This gives us a simple way to calculate time, for instance. Let us see what is 54 hours after midnight on some day. You divide by 24, you get quotient 2 and remainder 6. So that means it's 6 a.m. 2 days later. And this G is actually a group. Closure is obvious because G has all possible remainders on division by 24. Existence of identity, 0 is the identity, A plus 0 is equivalent to A modulo 24. Existence of inverse, A is in G, then 24 minus A is again in G. If you check it, A plus 24 minus A is 24, which is 0 modulo 24. So the inverse of A is 24 minus A. For example, the inverse of 3 is 21 because the sum of the two is 24. Similarly, the inverse of 20 is 4 because again the sum of the two is 24. Associativity is also easy to check. And G is a commutative group. So the takeaway from this exercise is, notice that for any non-negative integer, however large, for example 100,08793, on division by 24 leaves a remainder which lands up in G. Okay, now let us do weekly arithmetic. Let us say Sunday is day 0, Monday is day 1, Saturday is day 6. So G consists of 0, 1, 2, 3, 4, 5, 6, 7 numbers with addition modulo 7 arithmetic. Say, then we can ask, what is 1000 days from this Sunday? What day of the week will it be? So you divide 1000 by 7, that is 142, 6 by 7. So 1000 is equivalent to 6 modulo 7. So it has remainder 6 on division by 7, so it would be a Saturday. G is a group with the circle being addition modulo 7, which is denoted by equivalence modulo 7. Again 0 is the identity, 7 minus A is the inverse of A, and again it's a commutative group. So here's a homework for you. Can you find in day-to-day life some examples of groups? For example, look at periodic phenomena, look at nature, music, notes, tal. Write out G, figure out the group operation circle, find the identity, describe the inverses. Think of infinite groups too. Are your examples commutative groups? One last notion of subgroups. This also turns out to be very important in group theory. Notion of subgroups. G with circle be a group. Then you can take S circle to be a sub-collection of elements of G, such that S is a group as well with the same operation circle. S is called a subgroup of G. So that means all 4 conditions are satisfied by S as well. But S is a sub-collection of G. For example, in Z plus, take all multiples of 2, that is 0, plus minus 2, plus minus 4, and so on. Please check all the 4 properties. Similarly, again multiples of 3, and in general think of any integer n and multiples of any number n, and think of multiples of n, that means 0, plus minus n, plus minus 2n, and so on. It is again a subgroup. F cross into, for example, you can take both positive and negative powers of 2. For example, 1/8, 1/4, half, 1, 2, 1, 4, 8, 16. Can you now tell me why you have to take negative powers also? Okay, just think about it. And this is a subgroup under multiplication. Can you find other subgroups? For the clock arithmetic, G equals to 0 to 23, 0, 1, 2, 3 till 23, where circle was addition modulo 24. The subgroups are given by a procedure as follows. Firstly, the identity element is always a subgroup, right? You can check this. So that is one. Then find out all factors of 24, that is 2, 3, 4, 6, 8 and 12. Take one of the factors, look for multiples of that factor inside G. So the first subgroup is 0 with addition modulo 24. All the operations here are addition modulo 24. Then look for multiples of 2 inside your set G. 0, 2, 4, etc. till 22. That is a subgroup. 0, 3, 6, 9, 12, 15, 18, 21. That is, you look for multiples of 3 inside G. That is again a subgroup. 0, 4, 8, 12, 16, 20. Look for multiples of 4 inside G. Again a subgroup. 0, 6, 12, 18. Multiples of 6. 0, 8, 16. Multiples of 8. 0, 12. Multiples of 12. Okay. So these are all the subgroups of G. Find out all subgroups of the group G where G is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 with addition modulo 12. So these are all the remainders possible on division by 12. And can you find all the subgroups of this group? Thank you. Thank you for your attention.